Our next speaker is Marc Davis from MIT in electrical engineering and computer science, and he's going to tell us about quantum gate synthesis for Clifford+T circuits.
Thank you.
Welcome.
So my talk is about quantum computing. So first, I'll briefly introduce what is quantum computing. It's a kind of new emerging high-performance computing technology that takes advantage of the properties of quantum physics to perform certain computations much faster than a classical computer ever could. In a classical computer, you have bits that are always either in a 0 or 1 state. In a quantum computer, you have qubits that are in a superposition between the 0 and 1 state. And the way these superpositions work is when you measure a qubit, you get a 0 or a 1 with some probability, like a weighted coin flip. But when you measure multiple qubits at the same time, these coin flips have correlations between them that can't be explained by classical statistics. And that is the quantum part of a quantum computer. And in manipulating those correlations, that's how you can take advantage of the quantum effects to gain a speed up. So quantum gate synthesis is a technique that is used in the quantum compiling workflow. It is the process of taking a unitary matrix and deriving a quantum circuit that implements the unitary matrix. The unitary matrix is a little bit like a truth table in classical computing. It's kind of a high-level description of what you want your program to do, whereas the quantum circuit is the actual list of operations step by step, how to execute your program. The basic usage of unitary synthesis is simply to derive a circuit for a unitary that you want to perform but don't know how to do. But the size of the unitary scales exponentially with the number of qubits that you have. And so you can't use synthesis for very large circuits simply because you could never write down the unitary. However, you can use synthesis on smaller circuits and figure out a pattern in the circuits produced, and that can guide you to create algorithms that generate large circuits. Another way that synthesis is applicable to large quantum circuits is through resynthesis, which is taking your large circuit, cutting smaller pieces out of it, computing the unitary for each subcircuit, and then synthesizing that unitary. And now if your new synthesized subcircuit is more efficient than the original one, you can replace it, and you've now slightly optimized your larger circuit. But in order to optimize the circuit, we need to understand what we mean by more efficient. For NISQ quantum computing, which is running your quantum circuit directly on a quantum computer, as opposed to using quantum error correction, which I'll mention later, the kinds of gates that you have and the kinds of gates that you care about are dependent on what the hardware can actually do. Most quantum computers can do a parameterized single qubit gate. For example, superconducting quantum computers can do a RZ gate with an arbitrary angle. And that combined with some other single qubit gates lets you do any single qubit gate which is a continuously parameterized space. You also need at least one multi-qubit gate, and a common choice is the CNOT gate, which you can also do in hardware on a superconducting quantum computer. You can't quite do these gates perfectly, and so every time you do one of these gates, you add a little bit of error to your system, and that builds up over time. And the amount of error you get from the 2-qubit gates is typically more than you get from a 1-qubit gate, just because of the physics and the logistics of interacting 2 qubits as opposed to just modifying one at a time. So for NISQ quantum gate synthesis, we really want to minimize the number of CNOT gates. That's what we mean by an efficient circuit. NISQ synthesis techniques typically fall into one of 2 main categories. There's recursive matrix decomposition techniques. This is using techniques like the quantum Shannon decomposition or cosine sine decomposition to take a n-qubit unitary and break it into a sequence of n-1 qubit unitaries. And then you can repeat this recursively until you get to n equals 2, at which point you can use the CAC decomposition, which is known to give you optimal results for 2-qubit unitaries. These types of approaches tend to produce relatively long circuits, but be faster to run compared to the other main category, which is numerical optimization-based techniques. These take advantage of the fact that you have parameterized quantum gates that you can do. So you come up with an onsot circuit that includes some of these parameterized gates. You come up with an objective function, which is usually a matrix distance function between the implemented and target unitaries. And you use a numerical optimizer to tweak the parameters to minimize the distance between the unitary you're implementing and the one that you want to do. If the solution you get that way is not good enough, you can try again with the different onsots. And these types of techniques let you produce very efficient circuits, but are often slower to run. So one project I worked on was a good way of choosing the onsot circuits for your numerical optimization technique is by tree search. The way this works is that you start by trying an onsot circuit with no CNOT gates in it. If that doesn't work, then you try all the possible placements of one CNOT gate. And if those don't work, you keep adding more and more CNOTs until you eventually get a circuit that implements, that has a solution to implement your unitary. And because we searched this tree starting from circuits with fewer CNOT gates and building up, the first onsot circuit that does successfully implement the unitary will be one of the most efficient circuits that can do so. So now I'm going to introduce fault-tolerant quantum computing. When you build up all of the errors from doing your hardware quantum gates, that kind of puts a limit on how long your quantum circuit could be, because eventually you'll have so much error that your output is essentially just noise. So in order to get around that and run longer quantum circuits, we need quantum error correction, which is a technique where you can use many physical qubits to encode the state of one error-corrected logical qubit. And now, if an error happens to one of those physical qubits, that error can be detected and corrected using a quantum error correcting protocol, and it won't affect the actual logical qubit. However, there's only a certain set of quantum gates that you can perform directly on error-corrected qubits, and that's called the Clifford gate set. And the Clifford gate set is not sufficient for universal quantum computing. You need at least one non-Clifford gate. A common choice for that is the T gate. And you need a tricky technique to be able to get that into your error-corrected system. And that is called quantum gate teleportation. And that is a technique where you take the logical state that you want to enact the gate on, and you interact it with another specially prepared state that we call a magic state. And that lets you result in a state that's equivalent to acting a gate on your initial logical state. And that gate depends on what the magic state was. So now we've reduced the problem of doing a T gate on our error-corrected qubit to preparing the magic state that corresponds to the T gate with high fidelity. And that can be done fault-tolerantly through a process called magic state distillation. But magic state distillation is a costly process. It takes about 20 to 1,000 times as many resources in terms of working space qubits and runtime as it takes to do a Clifford gate directly on a error-corrected qubit. And so for fault-tolerant synthesis, we really want to minimize the number of T gates, and we actually don't care as much about the CNOT gates because CNOT is a Clifford gate and can be done directly. So there's a couple different types of fault-tolerant synthesis techniques. There are some that only work on single qubit gates. The Solovay-Kitaev algorithm is the oldest known quantum synthesis algorithm, and it actually can be applied to larger gates, but it doesn't scale very well. So in practice, it's pretty much only ever used for single qubit gate synthesis. A more recent algorithm is the Solovay-Kitaev algorithm, which is known to give you optimal approximations of any RZ gate, which is a type of single qubit gate. For multi-qubit gates, there are some techniques that can synthesize exactly multi-qubit gates, at least small ones, but not all quantum gates can be exactly done by Clifford+T. So instead, for some gates, you need to approximate it by finding a gate that can be done exactly that's close enough to the gate that you actually want to do. And there are some algorithms that do this, but they're typically limited in the number of T gates that they can do to about 20 T gates or so. So if you want to work with larger and longer circuits, a common approach is to work with the Clifford plus RZ gate set and then use the Sellinger-Ross algorithm to approximate those RZ gates as Clifford+T. And that's kind of the approach that I will follow, but I will use numerical optimization techniques to minimize the number of RZ gates that need to be approximated in this way. So when you're using numerical optimization for quantum gate synthesis, normally the objective function is a distance function between the implemented and target unitaries. This is kind of an artistic depiction of what the landscape of that objective function looks like. The actual function is highly multidimensional, and you can't really see all of the details in different local and global minima by looking at just 2 dimensions. But I hope that this would get the main ideas across. This is a function that has many both local and global minima. And it's actually periodic, and so every time there's one minima, that minima will repeat an infinite number of times. So in order to try to find the global minima, we really have to start with many different random starting points. Some will get stuck in the local minima, but hopefully some will get the global minima. There are techniques that guarantee you getting the global minima to a certain probability, but in practice, it's usually good enough to just pick a certain number of random starting points. Also, if your onset circuit can't exactly implement the target unitary, the global minima will always have a distance of 0, but in practice we set a threshold and accept any result within that threshold. When we're talking about fault-tolerant synthesis, our problem becomes a little bit different. We want to minimize the number of T-gates that can be used to implement the circuit while maintaining the distance threshold instead of just trying to minimize the distance. But minimizing the number of T-gates is not so simple. For certain RZ gates that have an angle that's a multiple of pi over 2, those are Clifford gates and can be done with 0 T-gates. For ones that are a multiple of pi over 4 but are not a Clifford gate, those can be done with exactly 1 T-gate. And for any other gate, you need to use the Sellinger-Ross algorithm, which will approximate it with a number of T-gates that doesn't really depend on the angle, but instead depends on the error threshold that you give, which is roughly 20 to 100 T-gates per RZ gate for reasonable choices of that error threshold. So this is a function that is really flat with sharp discontinuities at the multiples of pi over 4. That's not really something we can give to a numerical optimizer. So instead, we define a relaxed t-count function, which is really a triangle wave with valleys at the locations where we would like to guide our parameters. So to put it all together, we do a first optimization pass where we use a bunch of random starting points just to find some solutions that minimize the distance between the implement and target unitaries. We take those solutions, we give them to our second optimization pass, which is now trying to minimize the number of T-gates our circuit uses while still maintaining the distance threshold. Then after that, we find the parameter that is the closest to being one of those even multiples of pi over 4, and we round that parameter, and then we give it back to the first optimization pass to make sure that that rounding didn't make it so we can't meet our error threshold anymore. And we repeat this process until we've either removed all our Z-gates from the circuit, or we encounter a situation where we can no longer meet our distance threshold, in which case we undo the last rounding that we did and return the last circuit that worked. This process has been fairly successful in practice. I've been able to reproduce some of the best known T-counts for some common gates that can be done exactly as Clifford+T, and I've been able to reproduce best known RZ counts for some gates that can't be done exactly but can be approximated. And I'm currently working on the next step, which is scaling this to work on larger circuits through partitioning and resynthesis, which is taking a large circuit, cutting pieces out of it, optimizing those pieces individually, and then putting them back together. I'm still working on this, but as an early preliminary result on one of my test circuits that was a 256 qubit circuit, I was able to reduce the number of RZ gates by about 40%. So I'd like to thank my advisor, my collaborators, and of course CSGF, MIT, and LBNL that I worked with, and the Biscuit team at LBNL, which is their quantum synthesis group. And I'd like to thank you all for listening, and do you have any questions?